Ababutain, President and CEO of Daleelalma for trading.
Today I'm going to talk about viscoelastic material. In the name of Allah, most gracious, most merciful, I welcome you all to this presentation. This is an overview of my presentation. I'm going to show how important is this subject. Then I will define the viscoelastic material and how it deforms under stress. Then I'll talk about time and temperature effect on its behavior. After that, I will talk about the performance of this material at the laboratory and on site. What's the difference? The effect of glass transition temperature of this material. Then the overlap PVC tape performance. Then after that, I will show some data sheet tempering that some of the manufacturers are doing to make the data sheet misleading. Finally, I will give some examples of their failures in environment very close to ours. This is a study conducted in southern part of Mexico for a gas network for 10 years, and they found out that 2/3 of their failures are caused by external attack, external corrosion of their pipeline. This is another study conducted in Germany for 5 years, and they came with a conclusion that most of the failures are on pipe joints. So if we combine these two studies, we end up with a result that the most vital part of my pipeline is the girth weld external protection. This part of the project doesn't even cost 1% of the total project cost, and it defines the project's life. Now, viscoelastic material is also called non-Newtonian fluid. What is Newtonian? Newtonian is all these fluids that you see in front of you, like water, oil, honey. They obey Newton's law. That means the relation between shear stress. Is there a pointer here? This is the pointer? Okay. The relation between shear rate and shear stress is constant. This slope is the viscosity of the material. That means if I dip my finger in a water pour and run it at a certain speed, the drag I feel or resistance that I have on my finger is related to the speed by a constant value. That constant value is the viscosity of the material. So all these viscous material behavior is predictable. Whereas in viscoelastic material, what is viscoelastic material? It's a mixture. Visco comes from viscosity of liquid, elastic from elasticity of solid. So they are a mixture of both solid and liquid. Example of this is paste, mud, corn starch, cream, gel. All these are called viscoelastic because they are combined. You take a solid and put a water on it and mix it, you get a viscoelastic material that behave partially as liquid and partially as liquid, as I will explain here. There are 3 types of viscoelastic material. The first one is what's called Bingham plastic. What's the difference between honey and ketchup? If you open the bottle of honey and pour it directly to the gravity, the honey will for sure flow in 1 second, 3 seconds, 20 seconds, depend on its viscosity, but for sure it will flow by gravity only. Whereas in ketchup, you need to shake it or squeeze it, otherwise you will not get a flow. This is called Bingham viscoelastic material. The other two types are what we call shear thinning, or they call it also pseudoplastic. Examples of this is your toothbrush paste, or the mortar, the cement mortar. This is why when we want to transport mortar, we put it in a truck with a rotating drum to keep the viscosity low, to keep it soft. Otherwise, once we reach the site and start to bump it, it will not bump if we didn't shake it like that. Same thing, you feel it in mud. When you mix mud more, it becomes softer. This is called shear thinning. This is why. Now the third type is called shear thickening, or they call it also dilettante material, where the shear increases the resistance force of this material. All the viscoelastic coating you are using are from this type, this shear thickening or dilettante. This is an experiment that, or a material, a viscoelastic material made by Dr. Thomas Brunel in Queensland University. He put it in a funnel and isolated from the environment except gravity, and it gave him 1 drop every 9 years. What does that mean? That means at low shear, it is viscous, it is liquid. However, when he smashed it, I'm sorry, you can see it here, it is clear now here. If you smash it with a hammer, it shatters like glass or like ceramic. So when you apply a very strong shear, it gives you a strong resistance, because the relation is parabolic. As you can see, the relation here is parabolic. At high shear, the resistance is very high. At low shear, the resistance is even weaker than the viscous material. So imagine that you build your house from a material, from a clay or a mortar made of this material. And it looks okay, but in 9 years it is on ground. This is the viscoelastic dilettante material that you are using now in pipe coating. This is a glass transition temperature curve of this material. If you work here, you are okay, because first you are above the glass transition temperature. Second, because the effect of temperature is minimal on modulus of elasticity of the material. If you also work here, you are okay. But working here or there is a big problem. This is why I bet you that none of your supplier of viscoelastic coating will give you their melting temperature, because he don't want you to know that you are working within this range. In Alaska and Siberia, okay, because they are in this range, and I will show you what's the difference between working with viscoelastic coating here and there. If I ask you, can a person like me at ambient condition walk in water surface? Can I? You will say no. But from my knowledge as a KFUPM graduate and Virginia Institute of Technologies graduate and experience for 30 years as an engineer, I definitely say yes, I can. Why I can float in water? Because this crazy guy, can you run this video please? Can we run this video? Can we run it? Can I run this video? Okay, this is a crazy guy shooting a machine gun on a water lake at a dam in Saudi. And you can see the bolts are bouncing back. So if the bolts bounce back and the stress exerted by these bolts, I'm sure higher than the stress that I exert in water, Newton per millimeter, if it is bounced back, at least I can float. What do you say in this? I'm sure you all are saying it is wrong, but you don't know why it is wrong. It is because of the effect of time. If we go back here, see the time effect, the shear rate is time, So here is me walking on water. So I sink because the resistance is weak. Here is the bolt hitting the water surface. The resistance is high, so it pulls back. But what you didn't consider is that for dilatant material, the effect is much higher. It is parabolic. This is parabolic. What you are saying that I tested this viscoelastic material at my laboratory and it gave me a good tension, so I expect it to work on my pipeline for 30 years with the same performance. Not at all, not at all. I'll show you why. See, I talked about time, now it is temperature. This is a data sheet I took from one of these suppliers. At minus 45 degrees on steel, the field test is 20 Newton per millimeter. Once you increase the temperature by 70 to 23, this dropped to 1%, from 20 to 0.2, 1%, because of parabolic action. And here, if you increase the temperature 40 degrees more to 70, it goes to 1,000. It becomes ketchup. It's not a material with adhesion anymore. 0.2 Newton is not adhesion. It is ketchup. And this is the temperature effect on viscoelastic coating that you are using, that you are proud of using. Now to data sheet tempering. This here is catalytic disbondment resistance. I don't know whether you all know about catalytic disbondment, but if you put two material together, stick them together, and run a current between them, you will get a repulsion. That repulsion depends on the two materials plus the adhesion strength between them. So you need a very strong material adhesion to overcome the catalytic disbondment. However, these gentlemen saying it is 0. The real reading for them is 13 millimeter. This 13 millimeter is not acceptable by LACE. It is on the border of ISO, the European standard. Why they say 0? They wrote here for you not to read self-heal. What they meant is that after it's disbond, they disconnect the power, then the material will self-heal, will flow until it becomes 0. But in reality, catalytic protection never disconnected. It's always running. So it is this reading, which they are hiding in their data sheet. Another more detail, see here, they say at minus 45 degrees, where I show you the work is normal, it takes 90 days for the material to reheal, to float. And this is okay, very good. But at 23, as I showed you, the adhesion went down to 1%, it became one day. 1% of the viscosity lost. If you go to 70, they didn't write the right number. They say less than 1 day, less than 24 hours. Because 5 minutes is less than 24 hours. Or 1 hour is less than 1 day or 24 hours. And this is what they are hiding. It is viscous, it is ketchup at 70 degrees. This is what you are now installing in your pipeline and you expect it to work for 30 days. Go and inspect your pipes, which is under operation for 5 years, and challenge me if you find the same thickness up and down. Examples of viscoelastic material used in environments very close to ours. This is in Ecuador. Visco, I'm sure most of you know this Visco company. It sagged because they installed it in vertical position in 22 days. It sags in 22 days. And here in Primex, Mexico, it dripped in 8 months, even not 9 years. In 8 months it started dripping in Mexico, like our weather. And it is dripping here. Go and inspect your pipeline, it is dripping. This is a photo I took myself to a project in SWCC. See the sagging? The outer rod didn't hold because the outer rod only work under tension in radial position. But in axial, it loses. Here, because the geometry is inclined, it wrinkles. This is in Oman, in petroleum development Oman. I got their photos. See how much wrinkle in their PVC? This is a viscoelastic coating. And here the effect of UV for 2 months, after 2 months. Now, let us compare two coatings. One works very fine, the green one, in Alaska or Siberia or Moscow. But it affects by temperature too much. It doesn't make sense to use it in Saudi Arabia where the temperature is 40 to 60. Or rather we use this one, which is weaker here, but stronger in our condition. Last slide. I made a comparison between the viscoelastic coating data sheet, from their data sheet, and wishback tape coating. At 23 degrees, this is the standard of test. NACE is asking for 2.8 Newton minimum, and the ISO European is asking for 1 Newton per millimeter. Their result is 0.2, non-acceptable by both, and you approved it for your projects. You approved this material which is not acceptable by any standard. It is 20% of the ISO and less than 10% of the NACE, whereas the mishback tape is 3.5 on steel and 2.8 Newton per millimeter on coating and polyethylene tape. Thank you. By the way, that photo was me doing a will bullet in Saddam. Gentlemen, do you know what is Silibandi? Silibandi is a viscoelastic material, dilatant type that made for kids to play with, not to coat pipes, because it performs like solid, as you can see, under high shear, and like liquid at low shear. See, if you put high tension, it breaks. This is exactly the same material you are using on your 1 billion cost pipeline. Thank you.
Thank you very much. I'd like to welcome on stage our next speaker, Daleelalma. He's the Engineer and Account Area Manager at VR.